Okay, going to be doing a CFD analysis. It's a demo here for this. This is a 19-inch equipment rack-mounted box, 2 units, 2U, as a demo. So basically what I've done is we have a kind of a main board, 4 daughter cards. The daughter cards hold arrays of MOSFETs, so these are high power density components. So a little bit later when we actually add in the heat loading, these are going to be dissipating a significant amount of power. Over here is a cavity up BGA with a little heatsink heat spreader on top, and basically what we do is pull the air in up front through an intake, and then the air is exhausted out the back by this fan. So let's take a look. Okay. I'm gonna hide a few things here for clarity. All right. All right, so this is flow velocity. These are flow velocity vectors. Now I don't have any heat loading going on in the box. There's no heat transfer. Basically what I'm doing is just running through with a pressure drop. So I have an intake here. I have the fan exhaust at the back. And basically it's just driving a pressure differential through the box right now that drives the flow velocity. So what you'll see is actually, if in a full analysis, I wouldn't have the fan selected right away. Basically, what we do is set the intake at atmospheric pressure, and then vary the exit pressure over here. Just basically vary that over the anticipated CFM range for for the fan that you're going to be selecting, or for at least a group of fans that you have under consideration. As you drop the exit pressure, the airflow velocity through the chassis is going to increase. And when you plot that as a pressure drop versus CFM, this is going to give you a resistance curve for the system. Just with a grain of salt whenever you're doing this as an analysis. Based on experience, the actual curve that you will measure in reality tends to be higher. In other words, there's a greater flow resistance typically in a reality than you will see in an analysis. Typically by a factor of 1.5 to 2.5. Starts off at about 1.5 and goes up from there, increasing with design complexity. Typically I'll use 2 as a personal rule of thumb. So basically if I go through and create a pressure resistance curve for a box, I'll just multiply that by 2 times, and that band that's created between 1 and 2 is what I'll be using notionally to size for a fan. So based on the resistance curve and the amount of power you are trying to dissipate for a given temperature rise, you can select your fan. For this model right now, I'm just using a 70 CFM open airflow Mil 80 fan by Amatec Rotron. All right, so I'm going to take a look at some cut plots here. Okay. Let's go here. There we go. Okay, so basically the idea here, you can see there's a little baffle bracket that I've placed in here, but basically we're intaking here, air is being pulled out through the exhaust here. What I'm trying to do is maximize linear flow velocity, which is what you see here, feet per second, over these CCAs, over the tops of the CCAs where you have FETs, and then bring in the air once it goes over those, keep the flow velocity up over the heat sink so that we're making sure that the processor is getting good cooling airflow there. One of the nice things about this approach is we're only looking at flow velocity, so I'm not doing any heat transfer right now. That makes this analysis run quite quickly. So what you can do, one trick is if you can develop a flow profile over your card, At the macro level, using a simple pressure drop analysis, what you can do is take and make a smaller scale model of just the CCA, apply the airflow that you're seeing here over that local CCA, and you can cut your analysis time way down by doing that. So for this, I would look at the worst case card, probably this one here, and use that flow. And as long as we've got even power loading on these, and I'm meeting my junction temperature derating requirements on this one, I feel pretty confident there. Okay, so basically, this just gives you an idea for the flow. What we would do is apply heat loads and perform a component junction temperature and derating analysis. If there's sufficient margin, I'd probably look initially at reducing the size of this heat sink if possible, maybe offsetting it just a little bit more forward, just to make sure that there's no boundary effects or back pressure condition along the lower edge of the fan where this resides. All right. So that's one of the other things. Let's see here. To be cognizant of in this design as you get good airflow over the front here, I would keep any high dissipation components out of this back area just kind of notionally. My thought was I know where my heat loading is up here, and back here I'm going to be holding off on putting anything that's going to be a high power dissipator, or if I do, I'm going to have to redirect some airflow back there. Okay. I will be updating this analysis later, as discussed, to add in the power, heat dissipation, and do a junction temperature / derating analysis. But I'm going to shelve this for now to build up a structural analysis so we can talk about modal response, stress analysis, and fatigue life. So thank you much for your time.